It's not going. It's not. Oh, it's going. Yay! It goes. Okay. Hey, tell me what you were asking about again. Which number was it? 4. Okay. So the particle is constrained to travel on the x-axis and is initially traveling to the left. So it's initially going to the left with a speed of 10. So let's do that thing where we list out all the information. So his initial velocity is -10. Remember, velocity can be negative. Then there's an acceleration. It's rightward acceleration. So that's 2 meters per second squared acceleration. Until he's traveling to the right with speed of 20 meters per second. So firstly, there's 2 perspectives here we can take. We can just kind of think about like, well, how long would it take to go from -10 to +20 if that's how much you're increasing every second? What's the answer to that? 15 seconds. That's one way to think about it. The other way is just to say, I know there's an equation for this, right? It's my final velocity is my initial velocity plus acceleration times time. I find a lot of people are more comfortable with, say, a formula, right? It constrains your thinky winkies to like something very concrete. So my final velocity was 20. My initial velocity was -10. My acceleration was 2. Now, if you solve that, you get 15 seconds. Cool beans? Any questions on that? Now, the graphs are going to be a little interesting. What's nice is we can use this idea, right? Basically, and this is my final velocity, but what if I think of my velocity versus time function as just being v equals -10 plus 2t? That makes sense? So what does my velocity start at? -10. What number is that? 20. And there you go. That's what the graph looks like. And then the position graph, another one that's interesting. Now, where you started is arbitrary, but we typically want to start at the 0 position. That's usually what we want to do. So does the slope start off negative or positive? Negative, right? Because the velocity is -10. Then the velocity hits 0. Just for fun, just for fun here. What time is that? At what time would the velocity hit 0? Take 5 seconds, right? Plug 5 in there, you get 0. So then, therefore, at time 5, that's when I would actually hit my 0 velocity. The slope of my position graph would be 0. And then at the very end of this process, when we hit 15, I will have increased to, now my slope is +20. How do you feel about this graph here? Yes, no? Makes sense? Okay, so gravity. As I briefly mentioned yesterday, if you drop something, you've probably noticed in your life that it speeds up, right? The longer it falls, the faster it goes. So what's less obvious maybe is if you throw something up in the air, it is accelerating the whole time. So on the problem we just did, the thing was going this way, but the acceleration was this way, right? So what happened, it slowed down, stopped, and then ended up going forward. Make sense? Remember, it stopped at time 5. It's not clear. So let's look at dropping a bowling ball. And I'm just going to tell you, put a big box around that because that's the number we'll be using a lot this year. Negative 9.8. Okay, now that's called, acceleration due to gravity. Okay, so drop a bowling ball off a building. Here's the ground. Here's the building. Okay, you're gonna drop the ball. All right, and it takes 4 seconds to hit the ground. So let's use the same exact equation we used before. Your velocity is your initial velocity plus acceleration times time. Okay? So what's the initial velocity if you drop something? It's 0. Very good. That's not very obvious, right? Because gravity is pretty fast, acceleration is pretty fast. So when you drop something, you might think it's like shooting out of there with some speed, but it's not really how fast is it going right now? 0. So at some point I let go of it and that acceleration kicks in immediately. And so it only takes 1 second to go from 0 meters per second to 9.8 meters per second, right? That's what acceleration is. In 2 seconds, he's going almost 20 meters per second. That makes sense? So that's pretty fast, right? So after 2 seconds, the pen would be going faster than like Usain Bolt's top speed, like it was like 15 or something. Okay, so anyway, my initial velocity would be 0. My acceleration is negative 9.8 meters per second. And then it said the time that was in the air for was 4. So my final velocity down here, right before it hits the ground, would be 39.2, I think. Someone can check that for me with a quackalator. I think that's right. Now it's almost 40, because 9.8 is almost 10. Okay, anyway. That's the velocity. Now, technically, the question says speed. So speed is always positive, so I would just say 39.2 meters per second. Do we have any questions on that? No? Okay. Velocity versus time. Notice how I'm drawing the axes. That might help you. Now, the position graph is, I'm going to draw it like that. So this might require some elaboration here, but so my velocity versus time graph starts at 0, and it takes 4 seconds to go from 0 to, what number is this? Negative 39.2. There's my velocity graph. We okay with that? For position, now first of all, should this be an x-axis anymore? Not really. It's vertical motion now. So it makes more sense to either say y or even something like h for height. Make sense? Now, so your initial position, because could you call this initial position 0? and then have this be some negative position? Sure, you could. Or you could even invert your axes and say, this is the positive direction. There's nothing necessarily wrong with that. You just feel a little bit of a weirdo. Okay, so typically we're going to call the ground 0 position most of the time, unless there's some really good reason not to. So anyway, what's my velocity when this process starts? 0. So it's going to start off flat, and then my slope's going to get more and more negative until I hit the ground at time 4. So that's what that curve looks like. Time's going from 0 to 4. By the way, could you figure out how tall the building is using the same concept we talked about before? Yeah, roughly how tall is the building? Pretend this number was 10.
I'll say 40.
So call this 40, just for estimate purposes. Call this 40. It went from 0 to 40. So what was the average speed? 20. And how long did it travel for? It's about 80 meters. So the building was about 80 meters. It's pretty tall, yes. It's pretty tall. Taller than anything around here. Taller than you? Is that what you said? Yeah, it's taller than you, yeah. All right. Okay, 6, I was briefly on 6, let's talk about it. So 6, it's shot up with an initial speed of 50 meters per second. Okay, so in your equation here, that's 50. That would be negative 9.8. And reaching the maximum height, this part might not be very obvious, but when something gets to the maximum height, just what is the speed of the object when it reaches that peak? 0, right? Because it's going from positive velocity and changing from positive velocity to negative velocity. So it must be 0 in between there. So what you do for this one is you set your final velocity to 0 and solve for time. So you should find here that it takes a little bit more than 5 seconds, maybe 5.1, 5.2 seconds to reach the maximum height. Okay. And then on your velocity versus your graphs here, I'll show you the graphs just to avoid any confusion. Here you go. Here's the, I'm not sure if it's going to be that. Now again, there's some interpretation here where how long should this graph go for? Well, the way this question's phrased is you think we might just go from 0 to when it reaches its max height. So we started off with a velocity of 50. Is it 5.1? Is that correct? Or yeah. So about 5.1 seconds. Now this graph just shows going from coming out of the cannon to reaching its max height. If I wanted to show the entire story of it, meaning going from the cannon up into the air and then coming back down to the ground, I'd have to extend this, right? I'd have to have the velocity now going negative as the cannonball comes down. Position, he starts at ground level, right? Here's 5.1 seconds. And so think about this curve. What shape is it? Starts off with a big slope, 50 meters per second slope, and gradually levels out to about a 0 slope. Now again, this only tells you the journey from ground up to max height. If I wanted to tell the entire story, I would have to play the parabola. Here's a fun question. how long do you think it would take to hit the ground?
No, it would be 10.2.
Yeah, the time would be 10.2. Another 5 seconds by symmetry. So the time it takes to go from 50 to 0 under that acceleration, under this acceleration, is the same amount of time that it takes to go from 0 down to the same final speed. Now, of course, this is all neglecting what?
When you get your object.
Air resistors. So in real life, we all live in a fluid, air. So things don't, Now, if you're using a bowling ball for low speeds, something like a bowling ball is going to behave pretty much like there's no air. Whereas like a feather or a piece of paper, right? Like, oh, look, I've disproven Galileo. Like, I dropped this. It took longer for the paper to hit the ground than the rock I dropped. Well, that's because air resistance. But at high speeds, air resistance is really important, right? Because have any of you guys ever gone skydiving? Just curious.
I want to so
It's not that expensive, is it? Isn't it just a couple $100?
Yeah. I say we do that.
I know to get up to the point where you can do it by yourself is expensive. You have to do a lot of jumps, I think. But to jump with a certified person is not so bad.
Well, like plus if you can like a carry.
Oh, yeah.
There's one white fish.
Yeah? What is it, like $500 or?
I looked at less. I think it was at least 200, but it wasn't more than 5.
Okay. Anyways, I mentioned that because what happens if you're curious, as you're skydiving is, we'll be talking about forces pretty soon here, so just to kind of preview things to come. Well, what makes that acceleration? Where does that 9.8 come from? Well, I guess it depends on who you ask. If you ask Newton, he'd say, well, there's a gravitational force pulling you down. Einstein would say something different, but anyway, you're going this way, so gravity's pulling you down, and then the faster you go, air pushes back on you, the force from the air. But the faster you go, the more force this is. If you've ever stuck your hand out of the car window, you know that's true, right? The faster you're driving, the more force the air exerts on your hand. And so what happens eventually is this force ends up getting big enough that it cancels out this one. And now the forces are balanced, and that's what they call terminal velocity, meaning you can't speed up anymore. You've hit your max speed. So every different object has its own terminal velocity. Like a feather's terminal velocity is pretty slow. You can see it reach terminal velocity pretty quick. Bowling ball is going to be pretty high terminal velocity. You'd have to drop that out of a plane. I think a bowling ball could reach its terminal velocity out of an airplane. I'm pretty sure. Not positive though. A human can. You definitely. When you're driving, you hit terminal velocity, like you stop speeding up. Okay. Matchies. Let me move this here. So we're doing the matching thing. Hopefully the screen. Sorry, the screen's a little bright, but
Just like line it up. He's on the road with the scopes.
So, which of these graphs is a particle traveling to the right with constant speed? Notice every graph on here is a VT graph. They're all VTs, okay? So which one of these, so let's break this statement down. If you're traveling to the right, that means your velocity is positive, okay? And then constant speed means that your velocity is not increasing or decreasing. So which graph is it? Yeah, it's the middle top. So that first one is just. How about B? Initially at rest, so that means our velocity starts at 0 and travels to the right while speeding up. So if you're speeding up and traveling to the right, then your velocity is increasing. So that's going to be That's me starting at rest, and then this is speeding up. Okay. Part C, or sorry, description C, initially at rest. Now, okay, now you're traveling to the left while speeding up. Okay, so that can be a little confusing. But here's me traveling to the left, right? Now I'm speeding up. So think about what that means. Maybe initially I was going -1 meter per second, and then I was going -2 meters per second. So your graph, the screen might be unreadable. I'm not really sure. It looks really bright on this from my view. I'll move this. So if you're going left and speeding up, it looks like this. You're starting at rest. Now, tell me if that makes sense. So yeah, I'm going, it's more and more negative, but remember, negative just means left. So -10 meters per second is pretty fast. It's just going left. That makes sense? So that can be very confusing. You probably can imagine. Because I could say a statement like, the velocity is decreasing. It's a mathematical statement. The velocity is decreasing, but the object is speeding up. Think about that. D. So D would be the particle is traveling to the right and speeding up. So now by process of elimination, it doesn't specify that he started off at rest. So it could be something like this. So since we already ruled out the first choice, so which one on here? You guys can see it on your paper, right? So this is if all you know is that it's traveling to the right and speeding up. Oh, it's kind of suggested in the statement that it's starting off traveling to the right. Now a particle is traveling to the right and slowing down. What does that look like? Well, here's me traveling to the right. So I'm initially traveling to the right, positive velocity, and I'm slowing down, which means my velocity is getting closer to 0. Are you okay with that? Okay, F, traveling to the left. So I'm starting off traveling to the left. My initial velocity is already negative. And speeding up. So speeding up means I'm going which way? My velocity is moving away from 0. So maybe I used to be going -3 meters per second, and now I'm going -5 meters per second. I have sped up while going leftward. Now H and I have really long descriptions. Initially traveling to the right, but is experiencing a constant negative acceleration. So it slows down, momentarily comes to rest, and then begins traveling to the left with increasing speed. So at this point, process of elimination, we already have the answer, but so initially traveling to the right means I start here. My acceleration, is everyone cool with the idea that this point here represents me coming to rest momentarily? And then I'm going to the right, I'm slowing down, and then now I'm going to the left and speeding up. That's exactly what happens when you throw something up in the air. It's slowing down, speeding up. Slowing down, speeding up. That slowing down and speeding up was all caused by the exact same acceleration vector the whole time. And then, of course, I is just the opposite of this. Oakley, Cadokley? All right, this one. I really want to make sure we get to the new stuff today. It's taking longer. Here, let's try one more time. Sometimes the screen's visible. I'll just make these matchy lines extra wide. Okay, hopefully it's visible. So this first one, so now keep in mind, this is position, this is velocity. So look at this position graph. What is my velocity starting at? It looks like I'm going from a 0 velocity up to some positive velocity. So the answer to this one is that one. Next one. My velocity starting off, it's looking pretty negative. And yeah, a fairly sizable negative velocity. And and I seem to be doing, what's happening to my slope? It seems to be slowing down, right? It's getting less steep. So I need to find one that starts off negative and then like slows down. Starts off negative, velocity is approaching 0. This one, my velocity is starting off positive, and same effect. It's getting less slopey. Slopes are getting less steep. So that's that one. Velocity starts off negative, goes to 0, then goes positive. So I need to find one that goes negative, 0, positive. That's that. Then conversely, this one is starting off positive, hitting 0, then going negative. So that's that one. So that's the matching. There we go. There you go. So
you can see a cloud.
that's a good
Yeah,
show.
okay. As long as you do yesterday. Okay. Alright.
Yeah, so that's fine.
We did. Mr. Hall, maybe your comments about shooting the smoke actually is going to work.
Yeah, maybe. I say I'm more in favor of just maybe the protest. We'll just do a protest. We'll storm the office. Say we demand no smoke. Okay. So number 9. So I want to get through number 9 and number 11 today, and then these graphs, will be kind of like we've been working on them independently. So number 9 and 10 are kind of similar questions, so you might want to maybe leave yourself a note that 9 and 10 are pretty much the same question. So we'll do 9 together, and then 10 you can do on your own. 11 is a very important one, so we're going to go over that one today. Okay. The graph below describes the position of a hockey puck traveling in one dimension. And then it just clarifies that positive velocity corresponds to right traveling to the right. At around time 2, so right around here, right around at time 2, the puck is struck by a hockey stick. And the hockey stick only makes contact with the puck for a very short time. That would hopefully agree with your experience in real life, right? Like basically a baseball bat or a golf club, whatever, when you hit something like a hockey puck or a golf ball or a soccer ball, bat, whatever, the contact is only made for a very brief moment, right? So anyway, so interpreting this graph, what's happening between time 0 and time 2? The hockey puck is traveling to the right. Okay. So on what interval is the puck traveling to the right? Well, between time 0 and time 2. How about traveling to the left? 2 to 6. And we don't really care so much about, maybe even this makes more sense because we say, well, at time 2, it's transitioning between right travel and left travel. Let's find the displacement. So what is the displacement of the puck between time 0 and time 6? This one always stumps people. It's 2. Oh, very good. It's 2. Where did I start? 0. Where did I end up? Position 2, so the displacement is just 2 meters. If I want to show my calculation, it's 2 minus 0. It's 2. There you go. Distance traveled, though, a little bit more complicated, but not really. Yeah, I traveled 3 meters, right, between time 0 and time 2, so 3 meters. And then I traveled backward from 3 to 2, so that's 1 meter backward. But I treat it as positive because it's distance. There you go, 4 meters is my distance traveled. Next, what's my velocity at each time? What was my velocity at time 1? Let me give you a warning here. Don't focus your attention on that point. Focus your attention on this entire segment. Because yeah, we're asking about time 1, but isn't the velocity the same this entire segment? So all you gotta do is figure out the slope. What's the slope of that segment? 3/2, 1.5. So 1.5 meters per second, or you can write 3/2 meters per second. Then at time 5, same story. Don't try to like figure out where that point is. I mean, you could. It's at 2 1/4, I think, but we went down 1 meter and it took 4 seconds. So my speed there is negative 0.25 meters per second. Are we okay with that, guys? All right, here's the fun part. If the hockey stick was in contact with the puck for a period of 250 milliseconds, what was the acceleration experienced by the puck during that time?
Yeah.
It says 50?
Yeah.
Okay, we'll use 50 then. I don't know. That's weird. Strange. 50. I don't know. I'll have to make sure I have the right version of this. Okay, 50 milliseconds. That's fine. So what do you do? What do you do? So what are we solving for? Acceleration. Acceleration is the change in velocity over how much time that change took. So let's get our change in velocity. I went from what was it, 1.5? Do you see how this? Do you see my 1.5 is my initial velocity and my negative 0.25 is my final? So what I do is I subtract them. So it's negative 0.25 minus 1.5 meters per second over 50 milliseconds. What is that? So a milli, it's a great Lil Wayne song that explains all these things. Called a milli. A millisecond is a thousandth of a second. So this would be 50 thousandths. Does everyone understand that calculation?
Yeah.
So milli means a thousandth. A millimeter is a thousandth of a meter. A millisecond is a thousandth of a second. A milligram is a thousandth of a gram. Can I get any more? Let's see. No, those are the main ones. Oh, a milliliter. A milliliter is a thousandth of a liter. Anyway, so this number down here is 50 thousandths. Use a calculator. There's no need to like turn that into a decimal in your head or anything. Use a calculator if you're not sure how to do that. Okay? Now, so your calculator will then tell you, what do you get if you go negative 1.75 meters per second change in velocity? Over that, what do you get there? 35? 35?
Negative 35. Okay.
So your acceleration is negative 35 meters per second squared. Cool beans? Cool beans. All right, I guess we're running out of time. I'll have to cover. So your only homework, I guess, is to finish number 10. And tomorrow we're going to go over this. It's worth trying on your own. You might be, I mean, you'll learn a lot thinking about this one if you think hard about it. So anyway, but tomorrow we'll cover 11 and then all those other graphy ones.